Good morning. Today we are looking at one more chapter dealing with nuclear physics. So we're going to look at different additional types of nuclear reactions, and along with those we are going to look at the possibility, well, we have nuclear power plants that operate on what we call fission. So we'll look at some fission plants, and then we'll look at the possibility in the future possibly of fusion power plants. And then we'll also discuss a little bit about ways that we measure radiation exposure to high energy particles. And so let's go ahead and get started with this. We're going to start off looking at what are referred to as nuclear reactions. Now, up until now, the nuclear reactions we've looked at have been radioactive decay. So radioactive decay, you just start with something, it's just sitting there, and it's unstable in some sense, and so it's able to turn into something else, and so it breaks apart. In a nuclear reaction that we're going to be looking at here in the beginning of chapter 42, we're not going to be that patient. What we're going to do is we're going to set off reactions. So for example, there's an example of a nuclear reaction right here. It says what we're going to do is we're going to take some nitrogen-14 nuclei and some helium-4 nuclei, and we're going to run a reaction with them. Now, this is not like a chemical reaction, right? In order for a nuclear reaction to occur, either the helium-4 or the nitrogen-14 or both of these nuclei need to be moving really fast. We have to, in order to set off a nuclear reaction, it's going to be the nucleus of the helium, the protons and neutrons in here, reacting with the protons and neutrons in here. And so nuclei repel each other. They're positively charged. And so to set off a nuclear reaction like the one we have here, they've got to be moving really fast to overcome the repulsive forces. And if we go to high enough energies, we can certainly do this. So this is fairly routine now. We can create these kind of reactions. So again, it's not chemistry here. It's the nuclei and the protons and neutrons within the nucleus that are undergoing the reaction. Now, if you take a look at this reaction that they've given us here, this is kind of it's a good example to start with, I feel like. What's happening is I start with 2 protons and 2 neutrons here. And here I start with 7 protons and 7 neutrons. So what's that combined? 9 of each. And we're going to throw them together at really high speed. So protons and neutrons get all jumbled together. And then they're going to come away from each other. They might not be the same combinations. Some of the protons or neutrons might get exchanged. And so what happened in this case is, look, one proton all by itself came out. And that one proton is now getting labeled as a hydrogen nucleus. So I sent in a helium nucleus here, and here's a nitrogen nucleus. We ran them together. One proton ends up by itself. All the other protons and neutrons are here. So if we count how many protons and neutrons we start with and how many protons and neutrons we end up with, in these nuclear reactions, they match. Okay, so the number of protons going in, typically in the reactions that we are able to run in labs, it's unusual to have the protons turning into neutrons or the neutrons turning into protons. And so the numbers of protons and neutrons remain fixed, and that's kind of a characteristic of these kind of reactions. So it's transmutation, and when you think about it, it's converting these 2 elements into 2 different elements by allowing protons and neutrons to switch back and forth. Okay, here is that reaction in a fair amount of detail. Now, in this is the way I like the reactions to be written. So I'm going to say this is the way they've written, it's really useful. What will happen a lot of times is instead of saying helium-4, they'll write this as an alpha particle. They might even write this as ++, all right? Running into the nitrogen, And then this is what comes out of the reaction, and then there's a proton coming out. So protons can be listed as just hydrogen. Now what we want to do is we want to get a Q value. Now the Q value here is a little different than it was before. The Q value now is the combined mass of what we start with minus the mass of what we end up with. Before there was just one nucleus or one atom that we were starting with, but now in these reactions there's going to be two, typically. So I've got to take the two masses that I start with and subtract off the masses of what I end up with. I've got to count electrons correctly, something we learned in radioactive decay, beta decay in particular, and alpha decay too, I guess, is that correct electron counting is important. So what I'm going to do is I'm going to write everything as a neutral isotope. So I'm going to say that there's 2 electrons here, and 7 electrons here, and 8 electrons here, and 1 here, whether there are or not, because what that will do is it will balance the electrons. And in these reactions, in these nuclear reactions, all of the electrons are spectators. The electrons are not, whatever electrons go into the reaction, same number of electrons come out. So that means when I go to Appendix F and start looking up masses for the different isotopes, I look up the mass of the neutral isotopes. I don't subtract off any electrons. If I just don't subtract off any electrons, they will automatically balance out for me. Now that's in these nuclear reactions. What we saw in beta decay, that's not true. So in beta plus, beta minus decay, it's not that simple, but in these nuclear reactions it is. Okay, so doing this problem, I'm getting a negative value for Q. I haven't seen a negative value for Q. What does that mean? And what it means is that the mass of what we're ending up with is more than the mass that we started with. Somehow, we're creating something that has more mass than the reactants that we started out with. How is that possible? Well, what we're going to do then is these particles coming in are going to have to carry with them enough kinetic energy such that the kinetic energy can be converted into that additional mass. So let's see how we can diagram this out and kind of get ourselves organized to be able to calculate these kind of problems. So here's the Q calculation following the same format that we've done for Q's before. We got a minus number. Now what that tells us is that the mass of the helium-4 and the nitrogen-14 is here. What is that? It's like 18.0056. And then the mass of the oxygen-17 and hydrogen is like 18.007 or 8. So this is higher. I should have added those up and actually had the numbers. But you can add those numbers together, the 2 top ones and the 2 lower ones, and see that this mass is bigger than this. Okay, now what I've said is I'm trying to run a reaction where I get from here to here. And the difference in those, in terms of energy, is the Q value. And since this is minus 1.193 MeV, it says that the products are actually higher in terms of mass, and they're higher by the amount of 1.193 MeV. I would need that much additional kinetic energy coming into the reaction in order to create the final state, which consists of the oxygen-17 and the hydrogen-1. Okay. Now there's a second question that we already discussed briefly, and that is that there's what's considered an activation energy. I have to have the helium and the nitrogen coming in at high enough speeds that even though there's a repulsion that will take place. So as the helium and the nitrogen come in at high speeds, there's a repulsion between the nuclei, and they're going to slow down. I want them to at least just touch. So that's kind of a convention that we use to determine whether or not a reaction will be set off. we say that the two nuclei have to just touch. Now if you remember, the nuclei is this little tiny speck inside these atoms. And so by the time the nuclei are just touching, all the electrons are spread out all over. So it really does come down to individual nucleus, they're both positively charged. There's no electrons between them to help stabilize it. It's two positive point charges that have come in, or spheres of positive charge that have come into contact with each other. So two positive spheres, have we learned any formulas that would allow us to figure out how much energy that would represent? We go, yeah, that was the electric potential energy formula from chapter 23. That was, okay, it was a few weeks ago, but if you go back to chapter 23, oh, there's the formula. The potential energy that they will have is K, where K is the electric force constant, times Q1 times Q2 over R. Now, since we're looking at nuclei, the Q's, the charges, oh no, Q's are being used for two different things here. Okay, the Q's up there are the missing mass, right? It's the kinetic energy release. The Q's here are the charges on the two nuclei. So the helium nucleus has a charge of 2e, and the nitrogen nucleus has a charge of 7e. And if I take those two and I plug them in, what I'm going to get is a factor of 2 times a factor of 7 times Ke squared. Now, I don't think we've used this approximation yet. Let me see if I wrote it down here somewhere. I didn't. So when we get Ke squared together, it's easier if we don't use standard units. It's another one of our shortcuts. The combination of Ke squared is equal to 1.44 MeV times femtometers. So I'm going to say that's one of our shortcuts. We can use that. You can go back and use standard units if you want, but I think you'll find you're doing a lot more calculations on your calculator. So we can bundle the Ke squared together. And it always turns out to be Ke squared because the nuclei are going to be some integer number of e's. All right, so Ke squared, you can put that in. Now what I got to do is I got to decide center to center, how far are these spheres of positive charge, how far are they away from each other, center to center? And so for that, we're going to call this radius 1, radius 2. The combined distance is, I'm going to say R, R1 plus R2. And we can use the formula that we learned about back at the beginning of chapter 41. Back when that first section on nuclear physics, they said that the radius of a nucleus could be written as R naught, where, yeah, we need a couple more of these things written down. Anybody remember the value on R naught? So R naught, given in the beginning of chapter 41, was 1.2 femtometers. It should be here, but I didn't write it down. So that's 1.2 femtometers. Now the number of protons and neutrons in the helium-4 is 4. The number of protons and neutrons in the nitrogen-14 is 14. Those get cube-rooted. And that says that the effective radius of the helium, an estimate is 1.9 femtometers. For the nitrogen-14, it's 2.89 femtometers. I can add those together. And that's giving us, I rounded a bit, actually I kept more sig figs in my calculator. So the combined number worked out to be 4.80 femtometers. So I can put that in. Now notice, the femtometers in Ke squared are canceling the femtometers from below. Those drop out. And what I'm left with is a potential energy of 4.20 MeV. So that says the combined kinetic energies of the helium coming in and the nitrogen coming in would have to be at least 4.2 MeV. They've got to come in at high speed with lots of kinetic energy because they have to overcome the electric repulsion. So let's see, I need 1.19 MeV of kinetic energy to create the final state. But I need 4.2 MeV to overcome the electric repulsion between the nuclei. So that means that my diagram looks like this. I got to go up and over. That is my activation energy here. So this thing is 4.2 MeV in height, and that I'm going to write as U is this height, and then this is Q. So once we get the two to just touch, and that requires this much kinetic energy, then the nuclear reaction can occur, and then there can be a release of energy back down to the... so these guys are going to come flying out of the reaction. It's not like we're going to generate them and they're just going to be sitting there at rest. We're going to have 4.20 MeV to set off this reaction. So again, there's two items to keep track of. The electric repulsion, so we've got to calculate the potential energy, and then the other item is, do we have to have kinetic energy to create heavier particles? Okay, here is a deuterium reaction. Here's another example here. So we did that first example pretty thoroughly. Here's one more. Here is a neutron coming in, and it's going to react with the oxygen. Now the neutrons, as far as setting off a reaction, neutrons are great. Neutrons don't have any potential energy barrier. They're not positively charged. Neutrons can sail right through and reach the nucleus with no problem. So for this, I'm going to put the nitrogen and the neutron and the oxygen 16 at somewhere on my diagram, and then I'm going to calculate Q. So Q for this one, let's see, we're going to generate a nitrogen 15 and a hydrogen 2, which is also known as deuterium. So hydrogen 2, that isotope, has its own name. It's called deuterium. And when I carried out the Q calculation here, it says, yeah, once again, I'm creating something that's heavier. So I'm going to take that 9.9 MeV and this much height to create this. Now the good news is I don't have that big Coulomb barrier, but 9.9 MeV, that's a lot of kinetic energy to provide. So these things are going to have to, the neutron's going to have to come in with a lot of kinetic energy, and somehow the oxygen 16 is going to have to capture it. It's going to have to grab it and hold on. But it's going to come in with a lot of energy, and apparently this reaction occurs because the author of our book is actually a nuclear physicist who should understand these reactions. All right, so these are the reactions we're looking at. This is how we've been calculating the Q. If the Q is positive, then we release energy. If the Q is negative, energy is required. Here is another reaction where we're bringing in a neutron, this time to strike the nucleus of a boron 10 nucleus, and we're going to generate lithium and helium. Anything new we need to know? Okay, I think this is kind of similar to what we've done before. So here is the reaction written out. Everything's written neutrally. I looked up all of these masses, including the mass of a neutron by itself, calculated the Q's, same as before, mass of these guys minus the mass of these guys. Look, I got a positive Q value, and that tells us that the lithium-7 and the helium are actually lower in mass than the neutron and the boron 10, and they're lower by 2.79 MeV. So I don't need any additional kinetic energy in the reaction to get these to form. Now the other item is, look, I don't need any kinetic energy in the neutron because it's neutral. So I don't have any activation potential energy barrier to get through, and if I can just get the neutron in there, if I can get a beam of neutrons pointing at these boron 10 nuclei, this reaction should happen. Okay, now this, I thought, would be a good example for using maybe the formulas that we have developed to decide the speeds of these particles coming out. So what I'm going to do is I'm going to take not just the boron by itself, but I'm going to take the boron and the neutron combined and add their masses together as the starting mass. So we're going to imagine, maybe they told us this in the problem. Yeah, it's very slow moving neutrons. So we're going to treat the neutrons as if they're coming in with no kinetic energy at all. So for that, we can treat the starting objects, the starting particles, to be just at rest. I can add their masses together, call that m naught, and then m1 and m2 will be the mass of the lithium and the helium. What we can do then is we can plug those into the formulas that we've developed in special relativity, and the formulas we developed, I guess, we reintroduced in chapter 41. So if you're not already familiar with these, go back and see in chapter 41 where those were developed. But I can take these numbers then, or rather these numbers, let's say, plug them in very carefully. There's a lot of significant figures. I've got to keep track of them all. It says that 36% of the available kinetic energy will go to the lithium. The heavier lithium gets 36%. The lighter helium gets 64%. That's the energy they're going to get. And then I can use a little more. Now this is not relativity. This is relatively low speeds. And so I didn't use relativity. I took a classical formula, substituted in some factors of c, and then calculated the velocities using these formulas. So they're going pretty fast, but they're not going super fast. They're both, what, within a couple percent of the speed of light. I guess we could have done relativity to get this, but I used a classical approximation, which at these speeds should work really well. Okay, one more of these nuclear reactions. We've done a bunch, and we've done these pretty thoroughly. I'm going to take the proton. Notice in this one they said we're going to set off this reaction using a proton, but I'm going to take that proton and convert it into hydrogen 1 so that I have correctly counted electrons. Now I have 1 plus 6 electrons is 7, and there's the 7 electrons here. So these are the masses I want to use. I don't want to use the mass of the proton. I want to use the mass of hydrogen 1. The Q value turned out to be -3, so yeah, the stuff that we're producing is going to be higher in mass. And in addition to that, I've got to calculate the potential energy barrier. So I got to go back and calculate the electric potential energy using KQ1, Q2 over R. It's going to follow the same pattern of calculations that we did before. So I can take the atomic number of the 2 nuclei coming in. The atomic number for a neutron, I guess, is, I'm sorry, for a proton, for hydrogen would be 1, and then 6 for the carbon. This was my shortcut for Ke squared. And then the 1.20 femtometers, the hydrogen 1 is just 1 nucleon, and the carbon 13 is 13 nucleons. Now the protons that are coming in, they tell us in the problem, are 2 MeV, but look, the barrier is 2.15. So it's not going to be enough. They said that we're going to fire the protons in at 2 MeV, but the potential energy barrier is 2.15. Okay. So pretty thorough, I guess, with the nuclear reactions. Now, a couple of important nuclear reactions that date back to like the 1930s, and actually to the UC Berkeley, University of California, Berkeley campus here in the physics and the chemistry departments, running these reactions. They were able to take neutrons, fire them at uranium-238, and create uranium-239. Now, the uranium-239 undergoes radioactive decay, and it actually undergoes beta-minus decay, turning into element 93, which is not naturally occurring. So there is no element 93 left in nature. It's all decayed, whatever was formed billions of years ago in supernova explosions in this part of our galaxy. So, or it's decayed, let me say this, it's decayed during the lifetime of the Earth. And then that neptunium also beta decays into plutonium. So if you go up to the chemistry building, the old chemistry building, I want to say it's Gilbert Hall, is that right? Gilman Hall. Gilman Hall, I think, on the University of California, Berkeley campus. And you walk down the hall, there's a plaque on one of the doors that says, in this room was first isolated the first trans-uranium elements, neptunium and plutonium. So the physicists were running these reactions and taking their samples over to the chemistry department, and they were running chemical analysis to try and identify these new elements. Okay. All right, we're going to start talking about nuclear fission. So it turns out that if we take a nucleus of uranium-235, a particular isotope of uranium, and combine a neutron, we get an extreme nuclear reaction. Instead of just a little piece breaking off or something, the entire nucleus splits. And so it splits into not necessarily equal sizes, but sort of similar, two big pieces. And when that happens, those nuclei, there's more neutrons than can comfortably stay attached. And so we also produce free neutrons in the reaction. Now, what that means is there's going to be a lot of energy released in these reactions. So again, they're saying identify the elements here. So here's a neutron coming in. Here is a uranium-235 nucleus. One of the pieces that comes out is strontium-93. Excuse me. They tell us. And in addition, we have two neutrons left. So what would the missing isotope, what would the missing element be? And what we can do is we can fill that in. So what we want to do is say, I started with 92 protons. Fission is not going to change the number of protons. So if 38 protons are coming out in the strontium, then the remaining 54 protons are in that other element, and element 54 is xenon. Now, similarly, if I count all of the protons and neutrons together, that's 1 plus 235, that's 236. That number also has to be conserved. And so I'm just making sure the numbers add up. 93 and 2 would be 95, and the remaining missing number of nucleons would be 141. So we filled in that missing piece. Now what we want to do is let's go in and calculate Q. So this is what's considered fission. And again, what sets fission apart is that these pieces that are coming out, they're both pretty substantial. They're not, helium nuclei. They're big isotopes of relatively heavy elements. So here are the masses. I looked these up, or they were given to me, probably, in the problem, or I looked them up. Let's see. Xenon, I was just curious. I looked up xenon in the periodic table. It said that the stable isotopes of xenon are something like 134. So look how many extra neutrons this xenon is going to have. So that's what happens when you have something way at the end of the periodic table, like uranium, is going to have many, many surplus neutrons. And when it breaks into pieces and turns into two isotopes of maybe, half as much mass, you're not going to need all these neutrons to stabilize it. So the xenon has like 7 extra neutrons. That means this is going to start undergoing beta minus decay. It's probably going to undergo a series of beta minus decay. It's going to be radioactive. Similarly, the strontium, I looked that one up. It said the stable isotope for strontium is around 88. We have too many neutrons there too. So these both are going to start undergoing beta minus decay. There's just too many neutrons around, right? All right, let's get a Q calculation here. So let's take the masses of everything coming in, subtract off the mass of everything coming out. We've got all those labeled here. And we've got the missing mass and converting that into energy. It says that this one reaction, one occurrence of this reaction releases 181 MeV. Wow! When we had radioactive decay, how much energy was released? I don't know, a couple of MeV, maybe 4 or 5 in a really energetic decay. One fission is releasing 181 MeV of kinetic energy. So these are really, that's a lot of energy being released. Now, let's see what fraction of the mass has gone missing. So I'm going to call this the fraction of mass missing. And what I'm going to do is I'm going to take the energy that was released and divide through by the mass. Now I got to put them in the same units. So on this problem, I left the Q in terms of MeV. I should have just used mass. Anyway, I left the Q in MeV. I converted the mass of the uranium into MeV. It turns out that about 1 part in 1,200 of the original mass of the uranium-235 is now energy. So about 1 part in 1,200 difference in terms of mass. Well, that says that if we took 1 kilogram of 235 and we underwent fission processes, if we build a nuclear fission power plant and we bring in some fuel, just 1 kilogram of uranium-235, that would be enough to generate 7.4 10 to the 13th joules. And I looked at my PG&E bill to see how valuable 7.44 10 to the 13th joules of electricity is, and it's worth $4 million. So a kilogram of uranium-235 can generate $4 million worth of electric energy. All right. So, and that's the idea behind nuclear power plants. Nuclear power plants operate on the process of nuclear fission. Okay, now this is kind of an interesting table just because it shows if we took uranium-235, let's say we take uranium-235, we add a neutron, that makes 230. If this thing splits in half, that's going to give us fragments that have masses of what, 115, 120, something in that range. But when we run a bunch of these fission reactions and we look at what actually gets generated, and as you might imagine, the United States government and other governments around the world are very interested in this research. We actually don't get very many occurrences where we're right. It divides up 50-50. It's more common to get something in the range of between 90 and 100, and then having the other piece somewhere around 130 or 140. So it's more common to get a piece this size and a piece this size than to get 2 pieces that are identical. But that's just an aside for us. Just kind of interesting to see how that plays out. But again, I do want to go back. So when we run this reaction, as that next slide is showing, we don't get the same products every time. There's a whole range of different isotopes that can possibly be created in these fission reactions. But this is pretty typical. So getting about 180 MeV of energy from each one of the fissions, that's a pretty typical number. Okay, so 180 MeV per fission. Wow, that's a lot of energy. Okay, now notice what happened here also, that in order for the reaction to occur, the reaction required neutrons. So where are we going to get all these neutrons from? Well, it turns out that when the uranium-235 undergoes fission, there are more than enough neutrons that free neutrons are created, are released in the reaction. So in addition to these fragments, here are the fragments that, you know, the strontium and the, what was the other thing we saw? The strontium and the xenon. In addition, we're going to end up with additional free neutrons. And that means that the free neutrons can head off and set off other reactions. So we don't need a perpetual neutron source. We just need enough neutrons to get the process started. You know, it's possible you can set off the whole reaction with one neutron if this chain reaction continues. Now, what you realize then is, as long as the neutrons remain inside the nuclear reactor, then we're going to be able to set off additional fissions. But if they're lost to the outside, or if they're absorbed by material inside the reactor, that's going to slow the reaction down. So for a nuclear power plant, we would need to control the number of neutrons. Now what they point out here is, this is kind of remarkable. If we look at naturally occurring uranium, over 99% of naturally occurring uranium is the 238 isotope. It is not the 235 isotope, and the uranium-238 isotope does not reliably undergo fission. We need the uranium-235 isotope to reliably make this reaction continue. These guys all have to be uranium-235 nuclei. So how concentrated would we need to make the uranium-235 in order to have the reaction self-sustaining? And it turns out in power plants, we only have to get the enrichment up to about 2 to 3%. So in naturally occurring uranium, it's a little less than 1% uranium-235. It's like 0.7%. So we do have to undergo some enrichment. And you know, if you follow the news, you know that that's a big issue going on with nuclear weapons being developed in different locations around the world, and that for the nuclear weapons, they often involve enrichment of uranium. So what's happening is taking natural uranium sources that are less than 1% uranium-235. Now, if it's designed for a power plant, all you need is to enrich it up to about 2-3% concentration of uranium-235. Weapons would require a much higher concentration. So that's, you know, how do we determine whether a nuclear energy program is designed towards power plants or designed towards the development of weapons? You can look at the levels of enrichment in the materials. All right, so here is a nuclear, yeah, and this is kind of what we were just saying. So here's a neutron coming in. It sets off one of the fission reactions. A couple neutrons get generated. If these neutrons leave, I guess this is where the uranium is. Is that what it's saying? Yeah, I guess. So if these neutrons are lost, then it's not necessarily going to be self-sustaining. Okay, here's a full-blown nuclear power plant. So here's a nuclear power plant. Lots of, you know, here's the containment vessel. Lots of concrete here in case something happens. We want to make sure that we can keep the nuclear core, the reactor, separate. And of course, as you guys probably know, there have been some number, a handful of nuclear power plants that have failed. And the containment has not been completely successful. In some cases, it's only been partially successful. In other cases, it hasn't worked well at all, unfortunately. So the reactor core heats up. All this energy is being released through the fission of uranium. And what we're going to do is take some kind of a coolant. It can be something as simple as water or steam, or it can be liquid sodium. And that gets pumped through. and that carries the heat out of the reaction vessel. Now, it's important that this continue to be pumped at all times because there's an enormous amount of heat being generated. And if for some reason the pumping mechanisms fail, then the core will overheat. In addition to the fission reactions going on, there's a lot of radioactive product that's just sitting around inside that core, and those radioactive materials will undergo radioactive decay, and that will continue to generate heat. So you can see that even in the case where you do a shutdown and stop the fission reactions, you've still got the heat coming from all of the radioactive decays. So the pumping, the coolants must be pumped through those cores continually, even after you've shut down the fission reaction to carry away the heat from radioactive decay. So the heat that's carried in this water goes into a heat exchanger, generates steam. The steam turns a turbine, runs an electric generator. Let's see, this is chapter 18, this is chapter 29. This is more of chapters 18, 19, and 20. So a bunch of thermodynamics here, and also electric generators. So yeah, so it's a lot of the stuff that we've stored, and now we're looking at the reactor core itself and the fission reactions that are going on. Okay, here is the Chernobyl. I don't know if you guys have heard of this, but the Chernobyl reactor in Ukraine failed in 1986. The operators were trying some different configurations. They were trying different things with cooling the core, and allowed the core to overheat. And this did not have a very sturdy containment. The building itself it's a very early reactor. The containment building was not very strong. As you can see, the containment building just burst. There's a lot of hydrogen gas that can be generated inside these buildings, and a lot of radioactive material that was released. So, and there have been recent, I guess there's a recent series of, there's a documentary, right, going back and talking about Chernobyl and over the years how that has been managed. All right, so let's do a nuclear power plant calculation here, I guess. Estimate the amount of uranium-235 that would be needed to operate a 1,000 megawatt power plant. So here's our electrical power plant. Assume, from chapter 20, a thermodynamic efficiency of 33%. So let's see how much uranium we have to order for the year. So here's the power plant. It's generating electricity at a rate of 1,000 megawatts. Now 1,000 megawatts, a mega is 10 to the 6th, 1,000 is 1,000, so that gives us 1 times 10 to the 9th joules per second. Okay, that's how much electrical energy is coming out. Now during an entire year, a year is 31 million seconds, so if we take the 31 million seconds and multiply it by the rate at which this is the rate at which electricity is being generated. So it's 1 billion joules of electricity every second. Now the thermodynamic efficiency is telling us that for every 33 joules of electricity, we have to generate 100 joules of thermal energy. So that's how we've managed the efficiency. It's very easy to get that inverted. So I would say be careful with the units, pay attention to the units. What's the energy coming out versus how much thermal energy has to go in. And remember, we always need more thermal energy than the amount of electrical energy that's going to be generated. In any case, this worked out to be 9.58 times 10 to the 16. And then I converted from joules into MeV, and then I assumed about 180 MeV for every fission, every 1 uranium-235, and then I used the molar mass of uranium uranium-235. And what I've ended up with here is, for the entire year of a pretty good size electrical power plant, a nuclear power plant generating electricity, I just need a little over a ton of uranium-235. 1 ton, well, 1,300 kilograms. Now, if it was a coal-fired plant, how much coal would have to go into that power plant? And if it was coal, you would have railroad cars filled with coal coming through every day, right? Dumping off their coal, dumping that into the combustion chambers. But for nuclear power, we just need a little over a ton of uranium-235. That's remarkable, and that's why when you think about aircraft carriers or nuclear submarines, why would we want to power a submarine or an aircraft carrier using nuclear fission? Because all you need is the uranium-235. You don't need any oxygen to run this reaction, and all you need is 1,300 kilograms. Well, that was to operate an entire power plant for a whole year. So you don't need very much, and it's going to generate an enormous amount of energy. And for submarines, you don't need to have oxygen. So you don't ever have to surface. You can stay underwater. You can carry enough oxygen for the crew on board the submarine for a long, long time. And you don't need any for the nuclear power plant that's on board. Just very quickly, I looked up the density of uranium. I was wondering how big a block of uranium that would be. Uranium's really dense. Uranium's like, almost 3 times denser than steel. Its density is similar to like gold. And so if you run a density calculation, you can find out how big of a block, and it says a block of uranium that's 1,300 kilograms would be 40 centimeters by 40 centimeters by 40 centimeters. Okay, so 40 by 40 by 40 centimeters, that's enough uranium-235. Now, you wouldn't want to produce a block of uranium-235 that was pure, 100% uranium-235. You would want to keep the concentration low, fashion it into some fuel rods where you could place those fuel rods and put them into the reactor and control the contact or the proximity between the different fuel rods. Okay, and this is just reminding us that unfortunately nuclear weapons are usually an easier application than nuclear power plants. And so nuclear weapons, the early nuclear weapons exclusively used fission of uranium or plutonium as a fuel. There's another material, plutonium-239, which also reliably undergoes fission. And so nuclear weapons are based on those reactions. Let's see. So back when we were looking at an early part of chapter 41 at nuclear physics, what we said was that by combining light nuclei would provide a way to release energy. Now what we've been looking at here is fission, which is starting with something hot, heavy. And the binding energies here are already pretty high. By taking uranium and producing elements in this region, the energy differences are what the fission is releasing. So the differences in the binding energy, that's what's producing all this energy that we're looking at. But notice in the other direction, you could start with these lighter isotopes and combine them into heavier isotopes over here. And that would allow for potentially an enormous amount of energy being released. Now this is referred to as nuclear fusion. So reactions that we run kind of at the early part of the periodic table, one of the simplest reactions would be to take a proton and combine it with a neutron to form hydrogen-2. So this is referred to as deuterium. Hydrogen-2 goes by the name of deuterium. Now what also gets generated in this reaction is a high-energy photon, and that gets represented as a gamma symbol. All right, so here we are. Here is the reaction outline. So what we're going to do is we're going to take a neutron and a proton, and we're going to react those. And I think we're coming up close to a break. Maybe I'll run through this quickly, and after break we'll come back and review it a bit. So I'm going to take that hydrogen, that just represents a proton, combining with a neutron, forming deuterium and a high energy photon, a gamma particle. So those are the masses. Of course, the photon is massless. This is the mass of hydrogen 1, the mass of hydrogen 2, also known as deuterium, mass of a neutron. Now it says that this reaction, I do a Q calculation on it, and well, it's kind of standard. We've been doing these Q reactions a lot. And it's going to release 2.22 MeV. And since it's a neutron combining with the proton, there's no electric force repulsion going on. So it's just a straight release of energy if we can have neutrons combined with protons. Now I'm not sure if this is a high probability reaction. I'm guessing that this reaction might actually, just by having the neutrons and protons together doesn't guarantee that they will undergo this reaction, but we do have a 2.2 MeV, and that's a sizable amount of energy released in the formation of deuterium. All right, let's go ahead and take a break for 10 minutes, and then we'll come back and look at the rest of the chapter.